Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today, we are going to discuss about the module examples to evaluate the Clèche-Gordon coefficients from the paper Quantum Mechanics 1. The main points that we would be studying in this module are using the tables of the Clèche-Gordon coefficients, we are going to evaluate these coefficients. Then we will know the coupling of orbital angular momentum L equal to 2 with the spin S equal to 1 state and get the state J equal to 1 and M equal to 1. We will also learn the coupling of the orbital angular momentum L and the spin half of a particle, and we will evaluate the Clèche-Gordon coefficients for the same. We will know about the coupling of two spin half particles and evaluate the Clèche-Gordon coefficients for these cases. We would then compare this method of evaluating the values of Clèche-Gordon coefficients for the two spin 1 particles with the one already discussed and used in module 28. In this module, we study a few typical examples frequently used in physics for addition of angular momenta of two particles to illustrate how to use the tables to evaluate the Clèche-Gordon coefficients in the coupling of angular momenta. Specifically, we consider the cases 1. For the coupling of orbital angular momentum L equal to 2 with the spin angular momentum S equal to 1 to get the states representing J equal to 1 and M equal to 1. 2. For the coupling of orbital angular momentum L with the spin equal to half particles. 3. Addition of two spin half particles. And 4. Coupling of two spin 1 particles. The last example is chosen since this particular case has also been studied in module 28 to evaluate the Clèche-Gordon coefficients by using the lowering operator acting on the state with maximum value of projection quantum number m and getting the states with lower m values. Here we present a comparative study by directly using the table to get the values of the Clèche-Gordon coefficients. We shall give couple of tables obtained earlier for the relevant cases for ready use in the examples to be studied. Coupling of orbital angular momentum and spin. Example of addition of orbital angular momentum with spin of a system. Now let us see how we can use the Clèche-Gordon coefficients to find out the coupling between the orbital angular momentum and the spin angular momentum of a system. And this we shall do by taking some examples. So as a first case, let us suppose that we couple the state J1 is equal to L is equal to 2 to the state J2 is equal to S is equal to 1, so that the total value of the angular momentum J is 1 and the total value of the magnetic quantum number M is also 1. Now here in the example that we have considered, since the value of J1 is chosen to be 2 and the required value of J that we finally get is 1, the elements of the Clèche-Gordon coefficients corresponding to these values are given by J bracket open within brackets J1 minus M times J1 minus M plus 1 whole upon 2J1 times within brackets 2J1 plus 1 whole bracket close to the power half. And this is for mu equal to 1. For mu equal to 1, Clèche-Gordon coefficient comes out to be bracket open J1 minus 1 times within brackets J1 plus 1 whole upon J1 times within brackets 2J1 plus 1 whole bracket close to the power half. And for mu equal to minus 1, the Clèche-Gordon coefficient comes out to be bracket open within brackets J1 plus M plus 1 times within brackets J1 plus M upon twice J1 times within brackets 2J1 plus 1 whole bracket close to the power half. So using the above values for J and M and J1 and S, we get for the first term mu is equal to ms is equal to 1 and m1 is equal to ml is equal to 0. For the second term mu is equal to 0 and ml is equal to 1, and for the third term mu is equal to -1 and ml is equal to 2. And by substituting these values in the relations that I have just mentioned above, all the three elements of the Clebsch-Gordon coefficient corresponding to these three values of mu, that is mu equal to 1, mu equal to 0 and mu equal to -1, we get the corresponding elements as 1 upon under root 10, then minus root 3 by 10 and then root 3 by 5. Coupled state representing J equal to 1, M equal to 1. Now to get the physical picture of the example that we just discussed above, let us suppose that the eigenfunctions corresponding to J1 equal to L are the spherical harmonics given by YL, ML as a function of theta and phi, and the eigenstates for J2 equal to S are xi, S, ms, and the coupled state is represented by tau Jm. Now, as we have seen that the allowed values of all the quantum numbers are fixed, we can write down the coupled state in this representation as the coupled state tau 1 1, that is corresponding to j equal to 1 and m equal to 1, is given as under root 1 by 10 times y 20 xi 11 minus under root 3 by 10 times y21 xi 10 plus under root 3 by 5 times y22 xi 1 minus 1, where the subscript occurring in the spherical harmonics represent the orbital angular momentum L, represent the orbital angular momentum L and the magnetic angular momentum number ml, whereas the subscripts occurring for the spin part in xi represent the spin angular momentum s and the spin magnetic angular momentum ms, and the coefficients that we have got over here for the spherical harmonics and the spin term are the Clebsch-Gordon coefficients that we had evaluated above. Note that this representation is found useful in writing the state for deuteron, where we couple the spin triplet state with L equal to 2 to write the state for J equal to 1 and M equal to 1, corresponding to the non-central tensor force. Example 2. Coupling of L with spin half. This procedure can be extended to find the expression for the coupling operator Jm for any set of permissible values of J and M. Example 2. Addition of a particle of orbital angular momentum L and the spin s equal to half. To show how we can do this, let us refer to the table 30.2 that is given in the text of this module, and let us consider a particle of spin half having orbital angular momentum L, for which we use the quantum number J1. Let y, L, m, theta, phi represent the simultaneous eigenfunctions in the position representation of the orbital angular momentum L, that is the spherical harmonics, and xi half ms represent the spin states of the spin half particles. The allowed values of the total angular momentum J will be modulus of L minus half and modulus of L plus half, and of M equal to ml plus minus half, coupled states of L and spin half. Now let us represent the coupled state by the spherical harmonic Yjm, and using the second table for the Clebsch-Gordon coefficients, we have the value of the coupled state y subscript L plus 1 by 2 comma m given by bracket open L plus half plus m by 2L plus 1 bracket close to the power half y L comma m minus half xi half half plus bracket open L minus m plus half upon 2L plus 1 bracket close to the power half times y L comma m plus half xi half comma minus half. Here again y L m with different values of m and xi s ms with different values of s and ms are the spherical harmonics and the spin part that we are using, and the subscripts correspond to the value of L and ml for the spherical harmonic term, and the subscript correspond to the spin term s and the magnetic spin term ms for the spin term. Similarly, the other value that we get for the coupled state is gamma L minus half comma m is equal to minus of bracket open L minus m plus half upon 2L plus 1 whole to the power half times y L comma m minus half times xi half comma half plus bracket open L plus m plus half upon 2L plus 1 bracket close whole to the power half y subscript L comma m plus half times xi subscript half comma minus half. And as mentioned before, here the subscripts for the spherical harmonic term, that is y, represent L and ml, while the subscript for the spin term xi represent s and ms. And it is important to remember over here that the spherical harmonics as well as the spin functions are orthonormal eigenstates, and hence the two coupled states given by gamma jm obtained above are also normalized and orthogonal to each other. Thus, the equations obtained above are general in the orbital angular momentum L if, however, we consider a particular value of L equal to 1, we will have ml equal to plus half, 0 and minus half. Basically, what this means is that as we know that for each value of the orbital angular momentum L, the magnetic angular momentum term will have twice L plus 1 values corresponding to L, L minus 1 and so on to 0 to minus L minus 1 and minus L. So in this case, since L is equal to 1, therefore the values for the magnetic orbital angular momentum would be ml is equal to plus 1, 0 and minus 1. And the resultant values of J will be J is equal to L plus half to L minus half, where half is the spin term. So J will give you the values 3 by 2 and 1 by 2 corresponding to the value of L equal to 1. Spin 3 by 2 coupled states. Now corresponding to the total angular momentum J equal to 3 by 2, M can take the values twice of J plus 1. That is, if J is equal to 3 by 2, then the total values that M can take are 4, corresponding to M equal to plus 3 by 2, M equal to half, M equal to minus half, and M equal to minus 3 by 2, since the values of M, that is the magnetic angular momentum, lie between plus J and minus J. So, in a similar manner, we can see that if the value of the total angular momentum J is equal to half, then the corresponding M values will be 2, which are given by M equal to plus half and M equal to minus half. Therefore, in all, one will have a total number of 6 states, 4 states corresponding to J equal to 3 by 2 and 2 states corresponding to J equal to half. Now let us write these states explicitly. So for J equal to 3 by 2, the 4 states that we get, that is the 4 coupled states that we get, are given by gamma 3 by 2 comma 3 by 2 equal to y 1 subscript 1 comma 1 times xi subscript half comma half, where the subscript on gamma represent the first term in the subscript represents J and the second term in the subscript represents M. Similarly, for the spherical harmonic Y, the first term in the subscript represents L and the second term in the subscript represents ML. And similarly, for the spin term Xi, the first term in the subscript represents S and the second term in the subscript represents MS. So this was the first term for the coupled state. The second term for the coupled state corresponding to J equal to 3 by 2 and M equal to half is given by gamma subscript 3 by 2 comma half is equal to under the root 2 by 3 times y subscript 1 comma 0 times xi subscript half comma half plus under the root 1 by 3 times y subscript 1 comma 1 times xi subscript half comma minus half. And for the coupled state gamma corresponding to j equal to 3 by 2 and m equal to minus half, we have under the root 1 by 3 times y subscript 1 comma minus 1 times xi subscript half comma half plus root 2 by 3 times y subscript 1 comma 0 times xi subscript half comma minus half. And the fourth term that we get in the coupled state corresponding to j equal to 3 by 2 and m equal to minus 3 by 2 given by gamma subscript 3 by 2 comma minus 3 by 2 is equal to y subscript 1 comma minus 1 times xi subscript half comma minus half. Similarly, for the j equal to half, we will get two coupled state terms given by the first term corresponding to j equal to half, m equal to half, and given by gamma half comma half is equal to under root 2 by 3 times y subscript 1 comma 1 xi subscript half comma minus half minus under root 1 by 3 times y subscript 1 comma 0 times xi subscript half comma half. And the second term for j equal to half corresponding to j equal to half and m equal to minus half is given by gamma subscript half comma minus half is equal to under the root 1 by 3 times y subscript 1 comma 0 times xi subscript half comma minus half minus under the root 2 by 3 times y subscript 1 comma minus 1 times xi subscript half comma half. By writing these states explicitly, we can clearly see that given the orthonormal spin and the orbital angular momentum states, the coupled states are normalized and orthogonal to each other. Addition of two spin half particles. Example 3. Addition of two spin half particles. Now again, using the tables for Clebsch-Gordan coefficient and considering the addition of two spin half particles, we see that the total spin angular momentum S is summation of spin angular momentum vector S1 plus spin angular momentum vector S2 and can have the values 1 and 0 for the cases where we are considering half plus half, we get the value of the total angular spin angular momentum as 1, and where we are considering the case half and minus half, the value of the total spin angular momentum comes out to be 0. Now corresponding to this value of the total spin angular momentum 1, there are three projection quantum numbers for ms, because as we know that the spin magnetic quantum number ms has values, number of values given by twice of s plus 1. So if our value of the total spin angular momentum is 1, then the total number of values that the magnetic spin angular momentum quantum number can take is 3, corresponding to ms equal to 1, ms equal to 0 and ms equal to minus 1. While for the value of the total spin angular momentum to be 0, the values of ms can only be 1, and which corresponds to ms equal to 0. Now representing the spin half states of the two particles by xi half comma ms1 and xi half comma ms2, and the coupled states by xi subscript 1 comma ms and xi 0 comma 0, we write the spin states for s equal to 1 as xi subscript 1 comma 1 is equal to xi subscript half comma half particle 1 times xi subscript half comma half particle 2. So this corresponds to the case where the total spin angular momentum value is 1 and the value of ms is also 1. Now for the case where the value of total spin angular momentum s is 1 while the value of ms is 0, we get the coupled states as psi subscript 1 comma 0 is equal to 1 by under root 2 times bracket open xi subscript half comma half 1 corresponding to particle 1 times xi subscript half comma minus half 2 corresponding to particle 2 plus xi subscript half comma half 2 corresponding to particle 2 times xi subscript half comma minus half 1 corresponding to particle 1 whole bracket closed. And for the third case, that is for the total spin angular momentum value being 1 and the value of ms being minus 1, the coupled state is given by xi subscript 1 comma minus 1 is equal to xi subscript half comma minus half 1 corresponding to particle 1 times xi subscript half comma minus half 2 corresponding to the particle 2. Also, for the second case, that is when the total spin angular momentum s is equal to 0, we have only one value of ms corresponding to ms also equal to 0, and for this the coupled states are given by xi 0 comma 0 is equal to 1 by root 2 times bracket open xi subscript half comma half 1 corresponding to particle 1 times xi subscript half comma minus half 2 corresponding to particle 2 minus xi subscript half comma half 2 corresponding to particle 2 times xi subscript half comma minus half 1 corresponding to particle 1 whole bracket closed. Here the numbers given in the parenthesis are the particle numbers, and it is important to note that while the spin triplet, that is the s equal to 1 state, is symmetric between the interchange of particles 1 and 2, the spin singlet, that is the s equal to 0 state, is antisymmetric. Also, the state xi subscript 1 comma 0 is orthogonal to the state xi subscript 0 comma 0. Example 4. Addition of two spin 1 particles. Now let us consider the addition of two spin 1 particles. So let us consider the addition of two angular momenta j1 equal to j2 equal to 1. Let us construct the states j equal to 2, 1, 0 using the Clebsch-Gordon coefficients given in the table 30.1 of this module. Recall that in module 28 we also had studied this example and constructed the states with the help of lowering operator j minus operating on the state starting from the value of the projection quantum number m equal to 2 to get the state of the next lower m value. Proceeding this way, we obtain the values of the Clebsch-Gordon coefficients for different states. Here, we shall directly use the table of the Clebsch-Gordon coefficients and compare the two approaches. To construct the state j equal to 2, m equal to 2 from the given states j1 equal to 1, m1 equal to 1 and the state j2 equal to 1, m2 equal to 1, we find that the value of the Clebsch-Gordon coefficient from the table 30.1 is 1. Thus, we can write the state j equal to 2, m equal to 2 is equal to the state j1 equal to 1, j2 equal to 1, m1 equal to 1 and m2 equal to 1. Coupled states for j equal to 2, m equal to 1 and 0. Now the next coupled state that we are interested in finding out corresponds to the value of the total angular momentum j equal to 2 and the magnetic quantum number m equal to 1 and is obtained from the states representing m2 is equal to 1 and m1 is equal to 0 and the states m2 equal to 0 and m1 equal to 1. Now the values of the Clebsch-Gordon coefficients of these states are calculated by using the proper values in the elements of the first row of the table that we have for the Clebsch-Gordon coefficients, and if we put in these values in that table, then we get the final value for the coefficient, that is the Clebsch-Gordon coefficient, to be 1 by under root 2 for each of the states that we have discussed, that is for m2 equal to 1 and m1 equal to 0. Also the value comes out to be 1 by root 2, and for the state m2 equal to 0 and m1 equal to 1, also the value comes out to be 1 by root 2. Thus we get the total coupled state given by the state 2, 1 corresponding to j equal to 2, m equal to 1 is equal to 1 by root 2 times bracket open state 1 comma 1 and 0 comma 1 plus the state 1 comma 1 and 1 comma 0 whole bracket close, and this is the result that we had also got in the module 28. Now corresponding to the other case, that is when the value of the total orbital angular momentum j is 2 and the value of the magnetic quantum number m is 0, this coupled state is obtained by considering the states representing m2 equal to 1 and m1 equal to minus 1, that is one case, then m2 equal to 0 and m1 equal to 0, this is the second state, and the third state is m2 equal to minus 1 and m1 equal to 1. And if we put in these values of m2 and m1 for these three different states in the tables for the Clebsch-Gordon coefficients, then the corresponding Clebsch-Gordon coefficients turn out to be 1 by root 6 for the values m2 equal to 1 and m1 equal to minus 1. The value of the Clebsch-Gordon coefficient is under root 2 by 3 for the value m2 equal to 0 and m1 equal to 0, and the value of the Clebsch-Gordon coefficient is under root 1 by 6 for the value m2 equal to minus 1 and m1 equal to 1. Coupled states for the total angular momentum j equal to 2, 1 and 0. Now we look at the case where the coupled states for the total angular momentum j equal to 2, 1 and 0 are being found out, and we can write down the result for these states as the coupled state 2 comma 0 is equal to bracket open under root 1 by 6 times the state 1 comma 1 and minus 1 1 plus under root 2 by 3 times the state 1 comma 1 and 0 comma 0 plus under root 1 by 6 times the state 1 comma 1 and 1 comma minus 1, and these correspond to the three states that we discussed above. That is, the first term on the right hand side corresponds to the state where m2 is equal to 1, m1 is equal to minus 1. The second state corresponds to m2 is equal to 0 and m1 is equal to 0, and the third state corresponds to m2 is equal to minus 1 and m1 is equal to 1. So in this manner we get the result as was expected, and again is the same as the result that we had found out in the module 28. We can similarly proceed to get the states, that is the coupled states 2 comma minus 1 and 2 comma minus 2, and these are given by the representation. The coupled state 2 comma minus 1 is equal to 1 by under root 2 times bracket open state 1 comma 1 and 0 comma minus 1 plus state 1 comma 1 and minus 1 comma 0 bracket close, and the state 2 minus 2 is given by the states 1 comma 1 and minus 1 comma minus 1. Similar procedure can also be adopted to construct the states having the value of the total angular momentum j equal to 1 and the magnetic quantum number m equal to 1, and for this the coupled states are given as 1 comma 1 is equal to 1 by under root 2 times bracket open state 1 comma 1 and 1 comma 0 minus state 1 comma 1 and 0 comma 1 bracket close. Also for the value of the total angular momentum j equal to 1 and the magnetic quantum number m equal to 0, the coupled state is given by 1 comma 0 is equal to 1 by under root 2 times bracket open state 1 comma 1 and 1 comma minus 1 minus state 1 comma 1 and minus 1 comma 1 bracket close. And for the state corresponding to the total angular momentum J equal to 1 and the magnetic quantum number M equal to minus 1, the coupled states are given by state 1 comma minus 1 is equal to 1 by under root 2 times bracket open state 1 comma 1 and 0 comma minus 1 minus state 1 comma 1 and minus 1 comma 0, where the orthonormality is built into the relations that have been given. And finally, for the state with the total angular momentum J equal to 0 and the magnetic quantum number M equal to 0, we use third row of the tables for the Clebsch-Gordon coefficients and get the coupled state 0 comma 0 is equal to 1 by under root 3 times bracket open state 1 comma 1 and minus 1 comma 1 minus state 1 comma 1 and 0 comma 0 plus state 1 comma 1 and 1 comma minus 1 whole bracket closed. So students, now let us summarize what we have learned in this module. Firstly, we learned how to use the tables to evaluate the Clebsch-Gordon coefficients, and then once we learned this technique, then we applied this technique to find out the Clebsch-Gordon coefficients for the coupling of the orbital angular momentum L equal to 2 with the spin S equal to 1 and get the state J equal to 1 and M equal to 1. We also learned and found out the coupling of the orbital angular momentum L and the spin S equal to half of a particle, and we got to know that what were the values of the Clebsch-Gordon coefficients. Then we also learned about the coupling of two spin half particles and we evaluated the Clebsch-Gordon coefficients for the same. Finally, we learned about the coupling of two spin 1 particles to get the value of the Clebsch-Gordon coefficients and compared this method with the one already used in module 28. Thank you.